Hello everyone, myself Prashant Patil. Today we will see a new point of subject data structure. Before starting new point, just we recall the previous lecture points. Actually we discussed in previous lecture program development and their different steps. Also we discussed software development cycle phases which contains 5 number of phases. First one is requirement phase, second design phase, next analysis phase, refinement and coding, and verification and testing. These are 5 different phases we already discussed. Then we discussed refining an algorithm. Also we discussed algorithms are written in different levels, two different levels, data independent level and data dependent level. Also we seen different approaches designing an algorithm. First one is top down approach and the second one is the bottom up approach. Now we will see here next point of subject data structure. Before starting first point, just we seen which point we will discuss here. The first point is that complexity of algorithm. The second point is complexity in terms of constant, logarithmic, linear, quadratic, cubic and exponential. The third point is that complexity and execution time. And then last point is that time complexity. Now we will see complexity. Definition of complexity. A complexity of an algorithm is the function of time and space required to execute. It is called as complexity. Means that how much time and how much space is required to execute a particular algorithm, which is calculated by the complexity. Algorithm complexity is a measure which evaluates the order of the count of the operations which is performed by a given algorithm as a function of size of the input data. To put this simpler, complexity is a rough approximation of the number of steps necessary to execute an algorithm. Algorithm complexity, we cannot talk about efficiency of algorithms and data structures. It's without explaining the term algorithm complexity, which we have already mentioned several times in one form or another form. We will avoid the mathematical definitions and we are going to give a simple explanation of what the term means. Then we will see big O notation in short. Algorithm complexity is commonly represented with O of F notation, also called as or also known as big O notation. Means algorithm complexity is commonly represented with big O notation, which is called as O notation, where F is the function of size of the input data and the computational complexity, which is O of F, measures the order of the consumed resources, which is CPU time, memory, etc., by certain algorithm expressed as function of the input data size. Now we will see a next point. Complexity can be in terms of constant, algorithmic, linear, quadratic, cubic, exponential. This is respectively the order of constant. Logarithmic, linear, and so on number of steps are executed to solve a given problem. For simplicity, sometimes instead of algorithms, complexity, or just complexity, we use the term running time. Complexity means which is running time. Now see here, one table is there which contains three columns. First one is serial number, second one is complexity, and third one is the running time. Running time is how much time is needed to execute this particular algorithm, which is calculated by O of f, as we seen in the previous slide. The first one is constant, complexity is constant, and the running time is O of 1. The second complexity is that logarithmic. The running time is O of log n. The third one is that linear. The running time is O of n. The next one is quadratic. The running time is O of n square. Means this much time is required to execute this quadratic complexity of algorithm. The next one is cubic, O of n cube. And the last one is exponential, O of 2 raised to n, comma O of n up to O of n of k. First we will see constant, complexity, and running time is O of 1. It takes a constant number of steps for performing a given operation. For example, 1, 5, 10 or other numbers, and this count does not depend on the size of the input data, which is called as constant. The next one is that logarithmic. It takes the order of log n steps, means log n steps which will required when we execute logarithmic complexity, where the base of the logarithm is most often 2. For performing a given operation on n elements, for example, if n is equal to 1 lakh, an algorithm with a complexity O of log n would do about 20 steps with a constant precision, since the base of the logarithm is not of a vital importance for the order of the operation count. It is usually omitted. The next one is that linear complexity. It takes nearly the same amount of steps as the number of elements for performing an operation on n number of elements. For example, if we have 1000 elements, it takes about 1000 steps required. Linear complexity means that number of elements and the number of steps are linearly dependent. For example, the number of steps for n elements can be n by 2 or n into n steps required. Then we will see the next complexity is quadratic. It takes the number of n square number of steps, means n square means n into n number of steps are required, where n is the size of input data for performing a given operation. For example, if n is equal to 100, it takes about 100 into 100 means 10,000 steps are required. Actually, we have a quadratic complexity when the number of steps is in quadratic relation with the size of the input data. For example, For n elements, the steps can be of the order n into n square divided by 2. Then we will see cubic. It takes the order of n cube, means n into n steps are required, where n is the size of input data for performing an operation on n elements. For example, if we have 100 elements, then it takes 100 into 100 into 100, which is 10 lakh steps are required. The next one is that exponential, means raised to. It takes a number of steps which is with an exponential dependability with the size of input data to perform an operation on n number of elements. For example, if n is equal to 10, the exponential function 2 raised to n has the value 1024, means 1024. If n is equal to 20, it has the value 1048576, and if n is equal to 100, it has a value of a number with about 30 digits. The exponential function n is not equal to grows even faster. For n is equal to 5, it has a value of 120. N is equal to 10, then the value will be 3628800, and n is equal to 20, then the value will be minus -243290817664000. Then we will see a next point. The next point will be complexity and execution time. The execution speed of a program depends on the complexity of the algorithm. Means how much time is required to execute the particular algorithm, which depends upon the algorithm which is executed. If the complexity is low, the program will execute fast, even for a big number of elements. If the complexity is high, the program will execute slowly or will not even work for a big number of elements. If we take an average computer from 2008, we can assume that it can perform about 50 lakh elementary operations per second. This number is a rough approximation. The different processors work with a different speed, and the different elementary operations are performed with different speed. And also the computer technology constantly evaluates. If we use an average home computer from 2008, we can make the following conclusion about the speed of execution of given program depending on the algorithm complexity and the size of the input data. Then we will see time complexity. The time complexity is the number of operations or algorithm performed to complete its task, considering that each operation takes the same amount of time. The algorithm that performs the task in the smallest number of operations is considered the most efficient one in terms of the time complexity. The space and the time complexity are also affected by factors such as your operating system, means depends upon your operating system. Also depends upon your hardware, but we are not including them in this here discussion. Now, to understand the time complexity, we will take an example in which we will compare two different algorithms which are used to solve a particular problem. The first example is that example of time complexity is the first example is linear search. The problem is searching, we have to search for an element in an array. In this problem, we are going to assume that array is sorted in ascending order as we seen in the slide. The array elements are 2, 6, 7, 10, 12, 13, 16, 24, 27 and 30. Let us say the array contains 10 number of elements and we have to find the number 30 in the array. The search digit is, or the search number is 30. The array elements, as we seen here, the 10 elements are placed in contiguous memory locations. The index is starting from 0, 1, 2 up to 9, means 10 number of indexes are present over here. The search digit or the search number is 30. In linear search algorithm, we'll compare each element of array to search digit. Means that search digit or the search number 30 is compared with starting from 0th location up to the last location, means 9th location. The 0th location element is 2, means that search digit 30 value is compared with 0 location value 2, means 30 is equal to 2, no. Then goes to the next memory location, which is first. Let us count the number of operations it perform. Means here count the number of operations which are going to be performed. The first operation is 30 is compared with 0th location, again 30 is compared with first location, again 30 is compared with second location value, again 30 is compared with third location value 10, means 30 is greater than 10, then goes to the next memory location. Again 30 is compared with 12, then goes to the next location, because 30 is greater than 12, 30 is greater than 13, 30 is greater than 16, 30 is greater than 24, 30 is greater than 27, and 30 is equal to 30, means at the end, after completion of 10 number of operations, we will get the answer. Means let's count the number of operations it perform here. The answer is 30, sorry, answer is 10, because 10 number of operations are required here. Linear search uses 10 operations to find the given element. There are the maximum number of operations of this array in this case of linear search. This is also known as worst case of an algorithm. In general, linear search will take n number of operations in its worst case when n is the size of an array. Let us check or examine the binary search algorithm for this case. Now we can see here one array is there. The array elements are, I am taking same elements 2, 6, 7, 10, 12, 13, 16, 24, 27 and 30. These 10 number of elements are placed in array location starting from 0 to 9. Now here first we will understand what is meant by binary search. In binary search, the main rule is that the array elements are basically kept in sorted manner. Means it may be a ascending order or it may be a descending order. Now we can check here all the elements are in sorted or not. these all elements are in sorted manner, means ascending order. So we can apply here binary search. In binary search, first we have to take mid value, or to calculate the mid value. How to calculate mid value? Beginning plus end. Beginning value is 0 and the end value is 9. Beginning value is 0 and end is 9. 0 plus 9 divided by 2. Then we will get mid value. Now mid value is 4. Now 4 is a index of an array in fourth location, which contains the value 12. But our search digit or the search element is 27. Now search digit is compared with mid value. Means if 20 is equal to mid value is 12. Yes, condition is false. If mid value is greater than, search value is greater than mid value, then search at right side. If suppose search value or search digit value is less than mid value, then goes to the left side of an array. Now here 27 is greater than mid value, so we will search at right side of an array. Now see here 27 is greater than 12, so we will go to the right side of an array and again calculate the mid value. How to calculate mid value? Beginning plus end divided by 2. Now beginning of right side array is 5 and the end is 9. 5 plus 9, 14 divided by 2 is equal to 7. Now right side array mid value is 7. The location 7 contains the value 24 and the search value or search digit is 27. Now compare 27 is greater than 24. So again go to the right side of an array. Again calculate the mid value. How to calculate? Mid is equal to beginning plus end. Now beginning is, right side array beginning is 8 and the end value is 9. 8 plus 9 is equal to 17 divided by 2. The answer will be 8. Means here the mid value is equal to 8. Now I am going to compare search digit or the search number is 27 is equal to mid value is 27. Yes, number is found. Means that search value is every time compare with your mid value. If we try to apply this logic on our problem, now try to count the number of operations binary search took to find the desired element. It took approximately 4 operations. Now this was the worst case for binary search. This shows that there is a logarithmic relation between the number of operations performed and the total size of an array. I am taking here another one example of time complexity. The binary search example is that the array is that I am taking same array 2, 6, 7, 10, 12, 13, 16, 24, 27 and 30. All array elements are placed in the contiguous memory location, which assign index starting from 0 to 9. Now here the search digit or the search element is 6. As we know that we seen in the previous example, mid value is compared with search digit or search value every time compare with mid value. First need to calculate the mid value. How to calculate mid value? mid value is equal to, or mid is equal to beginning plus end. Now in this table, beginning is 0 and the end is 9. 0 plus 9, 9 divided by 2. The answer will be 4. Means we will get index 4 which contains value 12. Now the search digit or the search number 6 is compared with location number 4 value. 6 is less than 12. Okay, so 6 is less than 12, then we will see, or we will search, or we will go to the left side of an array. In left side of an array, again calculate the mid value. Means we will apply this procedure recursively, means repeatedly. Again calculate the mid value. Mid value is equal to beginning plus end. Now here the left side array end is 3. Now the beginning is 0, the end is 3. 0 plus 3, 3 divided by 2. The answer is 1. Now here the location 1 value contains 6 and the search digit is equal to, or search value is equal to 6. Means 6 is equal to 6. Yes, number is found. Means here 4 number of operations are required to find this particular value. This shows that there is an logarithmic relation between the number of operations performed and the total size of an array. Thank you.